Consider the Veil Nebula, a cloud of heated dust and gas located about 2,400 light-years from Earth, where a light-year is the distance light travels in 1 year, or approximately 9.5 trillion kilometers. The unique structure is the ongoing result of a supernova that occurred 8,000 years ago. The shock wave from the explosion is colliding with a cloud of gas and dust, creating rope-like filaments and a sheet-like appearance. Scientists compare newer images, such as this 2015 image from the Digitized Sky Survey, with detailed images taken by the Hubble Space Telescope in 1997 in order to understand the nebula expansion and other properties of astronomical objects. The forces that cause the supernova remnant to act as it does are the same forces we contend with here on Earth, whether we are planning to send a rocket into space or simply heating a new home. Although the scale is much different, the interaction of gases in the Veil Nebula resembles those on Earth, and the vibrant color combinations are created by the familiar glows of hydrogen, sulfur, oxygen, and similar elements that make up everything we know. Tonight, take a moment to look up at the stars. The forces out there are the same as the ones here on Earth. Through a study of physics, you may gain a greater understanding of the interconnectedness of everything we can see and know in this universe. Okay, so my name's Jason Harlow. And what I was doing just now is I was reading from a book called College Physics, published by OpenStax. It's the 2nd edition. I happen to have a paper copy, which I ordered online. But there's also an online version, and you can also download the PDF. It's a totally free textbook, so that's a good thing. So you can type College Physics OpenStax, S-T-A-X, all in one word there. Google it up. There it is, College Physics 2E. This takes you to this web page, and the whole book, like I say, is available. There's a table of contents. You can click on View Online, and unfortunately it asks you to give, so don't do that. Just go to your book. And look at that. That's right where we just were. It also encourages you to log in. Once I've logged in, it shows my little initials up there, and at this point I can actually do things like highlight, add little notes and things. This is so cool. And then when I come back and read that later, I can see my own little notes. So that's a cool thing. Another way to view this book, so they say recommended view online. I actually recommend you just download a PDF. So what that means is that it actually stores the whole entire book on your hard drive of your computer so that you can open it up on the subway or anywhere without any internet access and see the book, and there's no waiting or anything. And you can print little parts of it as you wish. So I'm just going to click the download button. It saves this PDF. And now when I open up a folder and click on wherever I put it, there it is. It's called PDF, College Physics something PDF. And then I can open it with Adobe or whatever PDF viewer I have. And there the whole thing is. Now it's a 1,697 page PDF, so it is a little bit long. But if you know that today's reading starts on page 23, you can just click on 23 and start from there. And I think it's nice to just send it to my printer if I want to, actually read a piece of paper, or I can read it on the screen, and you don't need the internet. So that's how I'd recommend it. So this is actually how we're going to look at for the rest of this video. Basic idea. All we're doing, starting on page 23 here, chapter 1, Introduction to Physics. We talked a little bit about the Veil Nebula already. It talks a little bit about the history of technological periods. Stone Age, Bronze Age, Iron Age were marked by our knowledge of physical properties of certain materials. This knowledge all stems from physics, whether it's the way a rock would flake when constructing a spear point, the effect of integrating carbon with iron in southern Indian and Sri Lankan furnaces to create the earliest high-quality steel, or the proper way to perfectly ground polished pieces of glass to create optical instruments. So And then the information age is based on little MOSFETs, which were invented by Muhammad Atala and Dahan Kang, metal oxide semiconductor and field effect transistors. So yeah, I mean, a lot of chapter 1 is giving you some history and some perspective and motivation on physics itself. So I'll just sort of scroll past some of this. There's a scientific method, really important to understand. Difference between a model, a theory, and a law. I would look at those since we're going to be using those a lot. I hate this image actually of the electrons going around it, because this is like the canonical kind of sciencey image, but in fact electrons don't do this. Any chemist who looks at this will be aghast, okay, because electrons exist in stationary states and probability density clouds. They don't go in tiny little circles with little strings around them like that. Okay. I'm just going to keep on scrolling along. Again, lots of history here. Some stuff about reminding you that what we're going to be learning in this course is what's called Newtonian mechanics, which has been around for quite some time now. But in the 20th century, there was something developed called modern physics, which includes two revolutionary theories, relativity. Einstein's relativity, developed in 1905, and later including gravity in 1915, and quantum mechanics, which was developed in the 1930s. These theories are the real physics theories that deal with everything, but you don't really need them. Newtonian mechanics is a good approximation to relativity and quantum mechanics, as long as things are kind of slow, like less than 1% the speed of light, and kind of big, like you can see them in, without a microscope. So that's good to know. And then section 1.2, we're getting into physical quantities and units. So again, I'll scroll through this kind of quickly, but there are things called units. This is somebody puzzling over what the unit of a cable is. It's a unit of length, I guess, but if you don't know what it is, then the map doesn't mean much to you. So there are standard units we use in science: meter, kilogram, second. There's some basic stuff about how the second and meter and kilogram were originally developed. Prefixes, hopefully you should know a little bit about this from high school, but kilo is 1,000, giga is mega is 1,000,000, giga is 1,000,000,000. That's for bigger things. If you're doing smaller things, then milli is 1,000th, micro is 1,000,000th, and nano is 1,000,000,000th. Okay. We're going to do unit conversions in this class. So if you wanted to convert 80 meters to kilometers, then you can actually multiply by a conversion factor which you know to be 1. So you know that 1,000 meters is the same as 1 kilometer. That's what the kilo stands for. So 1 kilometer divided by 1,000 meters, that's 1. So if you multiply this fraction times 80 meters, then the meters in the bottom of the fraction cancels the meters in 80. And so all that's going to be left is kilometers. And then you just take the numbers that you see here and multiply or divide them. If it's on the bottom, you divide. So you have to multiply 80 times 1 and then divide by 1,000. So 80 times 1 divided by 1,000. On your calculator, you get 0.080. And that's how many kilometers 80 meters is. So it's a good trick. We'll be doing some practice with that. So there's an example you see here on page 40. Should definitely work through that. Non-standard units, you might hear about these things like pounds, for example. Pounds can be converted to a unit of force, actually. We're going to be using newtons more. Section 1.3 is called accuracy, precision, and significant figures. It's called page 23, but on your PDF it's page 41. It starts off by talking about measuring mass. So there's a pan balance versus a spring balance. It talks about accuracy versus precision. One nice way I think some people look at that is this is a GPS. So the idea is that you're trying to find, using these radio waves that connect to satellites, your position, where the real center of the bullseye is your actual position, and there's 4 different measurements. If these are your 4 measurements that you see here, then that means that this is fairly low precision, but pretty accurate. If you look at the average of these 4 measurements, it's about in the middle. So we call that accurate. It's right, but it's just not super precise. Precise meaning a lot of decimal places, and accurate meaning close to the true value. It's also possible to be precise but not accurate. This is a smaller cluster of 4 measurements, but they're all wrong, right? They're all pushing you off in that direction. So it's not accurate, but the number of decimal places is higher or something. It's a more precise measurement. So the uncertainty kind of takes into account both of these things. If you have a very low uncertainty, we're hoping that the accuracy is good and also the precision is good as well. But really, uncertainty is what is used most often in science. We talk about an uncertainty. The uncertainty is this number, sometimes called delta something. So if you're measuring a quantity A, it'll have some units. Then the uncertainty in A is called delta A, another thing with units. So for example, if you measure the length of a piece of paper somehow with a ruler, you say it's 11 inches, you might say that your uncertainty is 0.2 inches. And then you'd write the length of the paper as 11 inches plus or minus 0.2. Then there's something called percent uncertainty, really important, which is just the fraction. So the fraction of the uncertainty divided by the value that you measure. And if you want to convert it to a percent, you can just multiply times 100. Okay, so next section is a very important one for your practicals. It's called uncertainties in calculations. So basic idea is that any time you make a measurement in the lab, it has an uncertainty, a plus or minus on it. But let's say you measure 2 things and want to combine them in some equation to get a result. Then the result has an uncertainty which is then based on the uncertainties of your input values. There is an uncertainty in anything calculated from measured quantities. For example, the area of a floor calculated from measurements of its length and width has an uncertainty because the length and width have uncertainties. How big is the uncertainty in something you calculate by addition or subtraction? Well, here's the example. If the uncertainty in x is ux, so that you report x plus or minus ux, and similarly, the uncertainty in y is uy, then if you either add these numbers, x plus y, so z equals x plus y, or z equals x minus y, or z equals y minus x, the uncertainty in the result is the square root of the sum of the squares of the uncertainties of the 2 numbers. This is called adding the uncertainties in quadrature. So that's addition or subtraction. The rule for how big is the uncertainty in something you calculate by multiplication or division. In this case, the percent uncertainty in the quantity is calculated by the quadrature sum of the percent uncertainties in the items used to make the calculation. Okay, so to put it in an equation, you can do this instead of percents, you can just use ratios. So if z equals x times y, or x divided by y, or y divided by x, then the ratio of uz to z is equal to the square root of the sum of the squares of the ratios of the individual errors to their quantities. So, for example, if a floor has a length of 4 meters and the width of 3 meters with uncertainties of 2% and 1% respectively, then you can calculate the percent uncertainty this way. The percent uncertainty is 1% squared plus 2% squared. Take the square root and you get 2.2%. So the area of the floor is 12.0 and expressed as an area, this is 2.2% of 12 meters squared is 0.264 meters squared, which we could round to 0.3 meters squared, not 0.4. So a high school track coach has just purchased a new stopwatch. The stopwatch manual states that the stopwatch has an uncertainty of plus or minus 0.05 seconds. So the team's top sprinter 1 week got sprinted the 100 meter at 12.04 seconds. The next week, 11.96 seconds. Can we conclude that this week's time was faster? So the book kind of just waves its hands and says, no, that's even wrong. We can compute the difference of times as delta t equals, just take the difference. You get negative 0.08 seconds. That's how much time he beat himself by. So, or they beat themselves by. So, is 0.08 seconds significant? Well, assuming that the stopwatch manual reports the only or significantly largest source of uncertainty, and there's no additional uncertainty due to the human pressing the stopwatch button, which is a big if, but if that's true, then you can calculate the uncertainty in the difference. You just take the sum of the squares. You're doing a difference, so you just take the sum of the squares of the uncertainties and then take the square root. So each time has an uncertainty of 0.05. So 0.005 squared plus 0.05 squared. Square root is 0.07. So that's the uncertainty of this difference. So the difference is negative 0.08 plus or minus 0.07. So I would say this is not quite consistent with 0. It's just sort of outside that 68% range there. So we can just barely conclude that this week's time is probably faster. So I might suggest to the authors that they change that solution. They just say, no, that's not true. So let's move on. Significant figures indicate the precision of a measuring tool that was used to measure a value. For example, 36.7 has 3 significant digits. There's the 3, the 6, and the 7. 3 indicating the tenths column, 6 indicating the ones column, and 7 indicating the tenths column. Special consideration is given to zeros. For example, in 0.053, we consider these first 2 zeros to be placeholders. They're just put there in order to indicate that this 5.3 doesn't mean 53. It means 500ths and 3,000ths, right? So since you're forced to put the zeros there, this is considered to have 2 significant figures. But if you were to say 10.053, then all of a sudden it's the zeros are not placekeepers there. They're part of what you measure. This is actually a very precise measurement with a 1/10,000th of uncertainty. So this is 1, 2, 3, 4, 5 significant figures. So you got to be a little careful with the zeros. Also, the zeros in 1300, we don't actually know. They could be placekeepers, or you might really know that it's not 1301. It's not 1300 or 1299. It's really 1300. It's a question is whether or not this number's been rounded to 1300 or not. So a better way to write it is using scientific notation. 1.3 times 10 to the 3, that's the same as 1300, but we know that that has 2 significant figures. 1.300 times 10 to the 3, again the same, but now we know this has 1400 significant, it has 4 significant figures. And when you use significant figures in calculations, if you're multiplying 2 numbers, the result should have the same number of significant figures as the quantity having the least significant figures entering into the calculation. So what that means is that you have to round it. So for example, maybe you have the radius of a circle has 1.2 meters. What's the area of the circle? Well, 1.2 squared times pi gives you this on your calculator, 4.52, et cetera, et cetera, et cetera. I guess this, if you wrote that down, I guess it would be fine, but it's sort of indicating a little more precision than you have. So you round it to 2. So you just do 4 and the 5, and then the 2 rounds down, so it's 4.5 meters squared. So in a way, it's a little more honest to say the area is 4.5 meters squared than to say that it's 4.5238934. For addition or subtraction, the rule is the answer can contain no more decimal places than the least precise measurement. And last section is called approximation. This is just in physics and in this class, I think it's good, a good practice to try to guess answers even before you do the calculation. And I'll talk about this a little bit. Sometimes I call it a sanity check, but sometimes you have a feeling for how big an answer should be, and if your answer you calculate is not that, doesn't match with your feelings, then that could be an indicator that something's wrong. Maybe your calculation's gone wrong. And it's good to check these things by approximating. And that's it for chapter 1. There's a glossary giving you some of the terms we used. There's sort of a summary, which can be helpful. And then there's a bunch of problems and exercises. Okay, Thanks very much. And when we come back, I'll start in on chapter 2. Bye for now.